Host Dr. Frank Summers of the Office of Public Outreach. And when you came in, hopefully you picked up one of these. These are our lithographs. And tonight's lithograph is the jets from a young star, Herbig Haro 24. We astronomers just call these HH objects, and they're really kind of cool. Now, I chose this one because just a few days ago was May the 4th. And those on the internet all call that Star Wars Day for the phrase, "May the 4th be with you." I figured some people in this audience hadn't heard that before. Okay. Anyways, so we had Star Wars Day last Saturday. And if you look at this Herbig Haro object, you can see the jets pointing away from the central thing, and we like to call this the celestial lightsaber because it has a resemblance to Darth Maul's double-bladed lightsaber, okay? Matter of fact, I have a blog post out there about the celestial lightsaber thing and relating and telling you what's actually going on. You don't need to read my blog post. You can just turn the lithograph over and read about it on the back there. And we've got a diagram showing you the jets from this young star. For those of you on the webcast, you can see the URL down bottom where you can get the PDF of this and have yourself and get to view it yourself. Tonight's speaker, the fiery fate of exoplanets. Ooh, burning death. Joleen Carlberg will be talking about this. Next month, we have recycle your used pulsars. Hopefully everyone does do this, at home in your recycling. If you got extra pulsars, recycle them because they can explain the extra gamma radiation from the central Milky Way. And Chris Britt will talk about that on June 4th. On July 2nd, Joe DePasquale, one of my colleagues in the Office of Public Outreach, will be talking about the art and science of astronomical image processing. These wonderful images that you see are prepared not by artists, not by scientists, but by combinations of artists and scientists, generally inside the same brain. People using both left and right brain to pull out the science, but also make it beautiful for the public to increase our understanding and appreciation. In August, we have the dreaded TBA, which is, Frank, you got to send out an email this month and get a speaker for August, okay? But I always do. When I do, I will post it on our website. And if you just take your favorite search engine and look for Space Telescope Public Lecture Series, you'll find this webpage with the list of the upcoming lectures over here on the right. And on the left, you can see our webcasting, the live links, as well as the past lectures back to 2014 on YouTube and back to 2005 on the STSCI webcasting. I will note that the STI webcasting just did a huge improvement, not only to the quality of their presentation, but also to the search capabilities on their website. I'm going to try and get somebody from STSCI webcasting to show that off next month for you, so when you go there, you can figure out how to find all those really cool lectures that we have been doing for, wow, that's 14 years of webcasting that they have of this public lecture series, okay? And finally, you can sign up for our email list there. If you do not want to sign up at the website, you can do as one gentleman did tonight. Give me a piece of paper with a email address on it, and I will make sure it gets added to it. If you have any questions for me or for the speaker about any of our organization, you can send them to the email address publiclecture@stsci.edu. Finally, if you would like to follow us on social media, we have a variety of things: Facebook, Twitter, YouTube, and Instagram, not only for the Hubble Space Telescope, not only for the Webb Space Telescope, but also for our institution, STSCI. I do a little bit of social media on Facebook and Twitter as Dr. Frank Summers. You can follow that if you like. And tonight, the observatory will be open. Yay! It hasn't been open for several months. Okay, so after the lecture, Matt from the Maryland Space Grant Observatory will be here, and he will take no more than 30 people, I think. Okay, so he can't take a huge group of 50 people. He can only take I think they prefer 10 to 20 people, okay? I'll let Matt figure it out afterwards. But if you would like to go across the street and go up into the Boris W. Offit telescope, and look at what's available, we can do so afterwards. Hang around afterwards. If I forget, remind me to say, hey, observatory, and people will gather probably over here and head out that door and go across, okay? All right. Now, our news from the universe for May 2019. Our first story tonight, wide and deep. So this is one of Hubble's most famous images, the Hubble Ultra Deep Field. And it is the deepest visible light exposure of the universe. And it basically, we see more galaxies in this tiny patch of sky than we see anywhere else. There are basically about 10,000 galaxies in this really tiny patch of sky. How tiny is it? Well, this is the ultra deep field compared to the full moon. Okay, all right. So it's about 1% of the full moon. There are about 100 patches about this size that make up the full moon. But contrary to what Hollywood may have taught you, the full moon's not that big on the sky. Here's a picture showing a wide field view showing, yeah, that's how big the full moon is in the sky. It's pretty small. Matter of fact, if you do the math, there are 12,746,784 patches the same size as the Hubble Ultra Deep Field on the sky. Okay? Hubble's field of view is 1/12 millionth of the night sky. So when we study the Hubble Ultra Deep Field, we're studying only one tiny little portion of the sky, and what we would really like to do is touch a much larger portion so that we can get the surety in our statistics. Okay? We want to be able to say what we see in this field is the same as what we see over here, as the same across the whole sky. So what we have done is, here is the Hubble Ultra Deep Field. This is the patch of the sky where the Hubble Ultra Deep Field. We have done mosaics and field studies. This is the GOODS, the Great Observatory's Origins Deep Survey, which roughly covers about 15 times the field of the Hubble Ultra Deep Field. And recently, what we released is something called the Hubble Legacy Field, which covers about twice as much as that again. So in this Hubble Legacy Field, they say, and I didn't count them, that there are 260,000 galaxies, okay? In looking at this patch of sky that's, looks like 30 to 50 times the size of the Hubble Ultra Deep Field, they're getting 260,000 galaxies. Now that gives you a lot more statistics, okay? Makes you much more clear about your understanding. And so this is the recent image that we released. It is actually massively huge. I tried working with it in Photoshop today. I was just trying to get these graphics here for the PowerPoint. Oh my God. It's like a 3.2 gigabyte individual image file, okay? It's just a lot of things. But because we are Hubble and we're paid for by your tax dollars, you can download every single pixel in this image, okay? All right, we have it at like 50,000 by 50,000 pixels available for you to download if you are so masochistic that you want to do that, okay? Astronomers will of course, be downloading this and doing lots of research studies on it. So finally, by getting to the Hubble Legacy Field, we do have an image that covers roughly the size of the full moon, okay? So maybe there's a few 100,000 patches of the sky, this size on the sky, but we're going from 1/12 millionth of the night sky to about 1,000th of the night sky, 100,000th of the night sky. All right, so you might think is this the maximum what Hubble can do? And I was like, all right, well, I think we've done something bigger than this. And I went through my images and such. I said, oh, yes, we have. So I found this image from a few years ago. This is, again, the Moon for Scale, HUDF GOODS, and the GEMS survey. And you can see the GEMS survey and the legacy field are pretty much the same size of the field, but the legacy survey is deeper, okay? So it's taking the GEMS survey data and augmenting that with even more observations, okay, in order to get this. So you could call the legacy survey GEMS version 2 and deeper, but the really big one that we did, which unfortunately does not go as deep as necessary to get those kind of statistics, is the Cosmos survey. And you can see that's, like 6 times the size of the full moon. So even though Hubble has a tiny field of view in the sky, 1/12 millionth, when you take these long surveys over many years, and Hubble's been up for 29 years now, you can end up getting some very large patches of the sky. And this is what we need to be able to do statistics. Now, just to blow your mind, the WFIRST, the Wide Field Infrared Space Telescope that we expect to launch in the 2020s, will be able to do the entire Cosmos survey in one image, okay? That's how big WFIRST detector is. It's 100 times the size of Hubble. Okay, it's infrared, goes a little bit into the red, but we have another telescope coming in about less than 10 years, hopefully, that will be able to do these really large patches in the infrared. So data is going to be huge in the next decade. Okay. All right, our second story tonight, Milky Way. All right, so what we're talking about is how do you weigh a galaxy? All right, we don't have scales big enough for it, okay? And even if we did, they wouldn't cover the mass ranges we have here. So when you're looking at a galaxy, in particular this spiral galaxy, you can sort of see that these spiral disks rotate, okay? I believe that this is a spinning disk. All right, so you measure a galaxy not by measuring the mass, but by measuring the motions, okay? So the motion of Earth around the sun tells you the mass of the sun because it's the sun's gravity that constrains Earth's motion. Similarly, the motion of stars and dust clouds and star clusters in a galaxy tells you about the mass inside a galaxy. And so if you measure these motions in close and all the way out, as far out as you can see in a galaxy, you can get a mass profile of the galaxy and effectively figure out how much mass is in there. Okay? And that's, looks pretty straightforward for an external galaxy that you can see like this. However, we're inside the Milky Way, okay? And we've got to go look and try and figure out, and we're moving inside the Milky Way, and you've got to deconvolve the problem from being inside the Milky Way. And whoops, that was the image I was supposed to show you, the Axel Mellinger version of it, okay? So we're inside the Milky Way. And to do it, it turns out that one of the best things to use are these globular star clusters. These are very dense star clusters. They're sort of gravitationally bound together, and they're sort of moving as a group together. So you can measure the motions of the stars, the bulk motion of the stars in these clusters, and use them to measure the Milky Way. So one component of this result comes from the Gaia satellite. Now, Gaia is an astrometric satellite. It's the most accurate astrometric satellite we've ever put up. 2 billion stars with their positions and their motions, etc., across the sky. Unbelievable data set that's still being developed and being developed more. And I think I showed you guys this shot when Gaia's first data release came out. This is their radial velocity map, and you can see over here in red on the right side, those are the stars that are moving away from us. And on the left side, you can see the blue ones, the ones that are coming towards us. And in the center, you can sort of see this flip, which is the motions internal to our motion through the galaxy. So Gaia has measured really carefully through the stars, the motions around the sun, and get a good map of the stars. But when Gaia goes to the globular clusters, it has measured a catalog of 34 globular clusters out to 65,000 light years, okay, which is a huge rate. It's much beyond the size of the Milky Way's disk. All right. But that's not quite good enough to get the full measurement because the Milky Way really extends out there. So, who are you going to call? Of course, Hubble got you, right? Hubble can have the fine resolution to see the globular clusters much further out. And so Hubble has started yet another dozen globular clusters out to twice the distance that Gaia can do, out to 130,000 light years. And if you combine the measurements from Gaia and the measurements from Hubble, then you can weigh the Milky Way with unprecedented accuracy. So here is what Hubble can do, and you can see the galaxies that are circled here. They're not moving, and what you're seeing are the stars that are moving, and these stars are part of this star cluster here. This is a deep part, tiny part of this globular star cluster, okay? And those tiny little motions that Hubble can measure can get you the bulk motions of those globular star clusters, all right? Together, Gaia and Hubble put together this is an artist drawing to give you the idea of all these star clusters extending out to 130,000 light years, and then you can extend that out even further to measure the full mass of the Milky Way. Now, previous to this, they had said that the best estimates were between half to about 3 trillion solar masses. And fortunately, the measurement from here is much more refined, but it comes down to 1.5 trillion solar masses. Okay, so that's million, billion, trillion, okay? 1.5 trillion solar masses. Now, if you know the number of stars in the Milky Way, the estimate of that is about 200 billion stars in the Milky Way, and the average mass of a star is about the same as the mass of our sun. So there's 1.5 trillion solar masses in the Milky Way, but only about 200 billion of that is stars, which indicates, as we've all known, that we're dominated here in our Milky Way by dark matter, okay? The unseen dark matter is the gravitationally dominant. We see it in other galaxies. We see it in our own galaxy, that the dark matter in the Milky Way is about 6 or 7 times more massive than the normal matter, the stars and the gas and the dust and everything. Okay? So why do we need to know this? The important thing is that we can see the Milky Way better than we can see any other galaxy. We have detailed measurements inside our galaxy, right? But we need to know how our galaxy scales against other galaxies in order to be able to apply this local knowledge to these distant galaxies. Having this measurement of 1.5 trillion solar masses allows us to take this knowledge that we gain locally and then apply it more accurately to external galaxies. So we have been able to make a more accurate measurement and able to weigh the Milky Way. All right? Okay, any questions before we go on?
Way compared to other galaxies?
Good question. How does the Milky Way compare to other galaxies? Well, the Milky Way at 1.5 trillion solar masses is relatively normal for a large galaxy. Of course, we have some dwarf galaxies around us, the Large Magellanic Cloud, Small Magellanic Cloud. They're a few billion solar masses, okay? So they're, 1/1000th the size of our Milky Way. There are some giant elliptical galaxies that are about 30, 40 trillion solar masses, okay? So they're 10 to 20 times the size of the Milky Way. So we're in the large galaxy, we're not in the extra large, but we're certainly not in the dwarf size, okay? So we fit in reasonably well, okay? Yes?
As you expand those deep field, is the density of galaxies about the same?
As we look at different pieces of the sky?
Yes.
Yes. When you take an observation, all right, so the question is the density of galaxies the same in all these different deep fields? When you take an observation to the same depth, okay? So, if you go to, I think the deep field goes to almost 30th magnitude. That's how, and if you take another 30th magnitude deep field, you get similar numbers of galaxies, yes. We have not seen any discrepancy from the number counts in this direction over here, and the number counts in this direction over here, and the number counts in this direction over here. They all seem to be, roughly the same. Now, they're not exactly the same, of course, but, minor variations. We do not see any large variations in that. Okay? All right, thank you for the questions. Let me bring up our speakers. Okay. Our speaker tonight is Joleen Carlberg, and you work on STIS. Which group is that in? It's INS. INS. We have all these acronyms, and I've got to tell you, I don't pay attention to every single one of them. But she works on the Space Telescope Imaging Spectrograph and the User Support Group. And we were talking about this yesterday, and she does amazing work to help the astronomers who are using Hubble to understand exactly how to use it and get the maximum science. But the folks in our building not only do their functional work like that, but they also do their amazing science, and she'll tell you about it tonight. Ladies and gentlemen, Joleen Carlberg.
All right, thank you very much. I'm really excited to come here today to talk to you because it's one of my absolute favorite things to talk about, which is how exoplanets are going to be consumed by their stars. So I think right now is a very exciting time in the world of astronomy because right now we know of thousands of planets, exoplanets, orbiting stars other than our sun. And because of this wide number of planets that we know, we have found worlds that are very different from our own. We have found planets that are unlike anything we would have imagined nature being able to put together. And we're able to see planets around their stars at various stages of their stars' lives, which allow people like me to do my research and try to think about what is going to happen when the stars evolve and what is going to happen to their planets. So throughout this talk, I'm going to be covering a couple of different things. First, I want to talk to you a little bit about what we know about the population of exoplanets that we have discovered thus far. And then I'm going to talk a little bit about basic stellar evolution so you can get an idea of what the overall life cycle of a star is so that you can have a better sense of how it impacts the planets around it. And then I'm going to talk more about the meat of my talk, which is the actual ways that planets are going to be destroyed by their stars, which is very fun, if not a little bit morbid. And then I'll kind of wrap up and try to give you a sense of some of the really exciting things that I think are coming down the pipeline in the next few years. Frank talked about how there's going to be a plethora of data coming in the next 10 years, but I think we're really there already. And even in the next 1 or 2 years, we're going to have a fire hose of data coming in. All right, so just some basics of exoplanets. There are really 2 key characteristics that astronomers like to think about when we characterize planets that we discover. One is how big they are, and this can refer to either the mass of the planet or its physical radius. And the other is the distance of the planet to its star. So if you follow news articles about the latest discoveries that astronomers have on exoplanets, you will frequently hear terms like a hot Jupiter or a warm Neptune or a cold this or warm that. And really what this is trying to convey to you is roughly how big is this planet and roughly how close is it to the star. So the hot, warm, cold is telling you, is it really close by and getting cooked, or is it so far away that the star's light really doesn't matter? Now, what I'm plotting here is our up-to-date knowledge as of a few weeks ago of all of the confirmed planets around other stars. I'm going to take a few minutes to explain the axes here. So on the bottom, which is a little bit more cut off than I was hoping, is showing the separation of a planet from its host star. And on the y-axis, I'm showing how massive the planet is. In this plot and a lot of the plots that I'm showing, the axes are going to be logarithmic, which means they're going to be stepping in powers of 10. So in this case, 1 refers to the separation of Earth from the sun, and we'll step in powers of 10 times farther and 100 times farther, 1/10, 1/100th, etc. And the y-axis here is scaled to the mass of Jupiter. So 1 here is the mass of Jupiter. These are 10 times more massive, 1/10, 1/100th, etc. So the big circles that I've drawn on here are the planets in our solar system. And all of these other colored points are the planets that we know that exist around other stars. The color coding of the points tell you how the planets were discovered. And you'll notice that this large swath of pink triangles these were discovered by the transit method, the vast majority of them by the Kepler telescope itself. Now, you'll notice that there still aren't very many things that we've discovered that look like the planets in our solar system. But the reason for that isn't necessarily that they don't exist. It's the fact that things that are in the top left portion of the plot are just easier to find. So the more massive you are, the bigger you are, the easier it is to find. And for most of the techniques that we've used thus far, the closer you are to the star, the easier they are to find. And so this drop off in this direction is just because we can't find anything. However, what I would like to point out, for starters, is this huge grouping of planets right here, which you'll notice our terrestrial planets sit below this box and our ice and gas giants sit above. So Kepler has discovered this class of planets for which we have no examples in our solar system. And so you'll hear terms like super Earths and mini Neptunes to describe the fact that we don't really know exactly what we expect for the composition and structure of these planets to be. And so I think these are a really exciting thing that Kepler has discovered. And these things are intrinsically abundant. Because like I said, these things are easier to find. So the fact that we find so many down here and they're harder to find means they are much, much, much more common. However, I do also find things in this box to also be extremely interesting. These are one of the first types of planets that astronomers discovered, which we termed hot Jupiters, which we didn't expect at all. So these are things as massive or sometimes more massive than Jupiter that are sitting at distances that are significantly closer to the star than Mercury is. And so why I think that's interesting is that if we drop poor little Mercury into the sun, we might not expect much to happen. But if you start dropping things that are the size of Jupiter or bigger into its host star, you might actually have a chance of seeing the effects of that engulfment by studying the star itself. Okay, so I promised to tell you a little bit about the different types of stars and how they evolved. So this representation here is a very famous Hertzsprung-Russell diagram, which plots lost my pointer here, which plots the temperature of the star from hot to cool versus the intrinsic brightness of the star from dim to very bright. And we discovered that the majority of stars fall along this diagonal line, which is termed the main sequence. This is where stars will fall when they first become stars and are fusing hydrogen to helium in their cores. And this is a mass sequence. These are very massive things. These are very low mass things. But then as the stars evolve, they will eventually become the type of stars that I like to study, which are red giant stars. And these are the stars that I'm going to be talking about a lot throughout this talk. Now, to give you a sense of what we may or may not know about these stars, I'm going to run this animation showing how stars evolve. So at the very beginning of this animation, all of those stars fell along the main sequence because the model was initiated for when all of these stars originally became stars. And you'll notice that the top part of the diagram, these massive stars, evolve off really quickly. So massive stars have short lives. And you'll see when they become giants, they pass out of this region really quickly. So that the main sequence lifetime is relatively long, but when stars become red giants, they don't stay there for very long before they continue on and die. So if you took a group of stars that formed all at the same time and observed them sometime today, the most massive star that is still a main sequence star gives you a rough sense of how old that population of stars are. And all of the stars that are currently red giants are actually almost all of identical mass. And this is just to give a representation of just how big stars get when they become red giants. So down here in this little corner, if you can see, is our sun. And to scale are the sizes of some well-known red giant stars that are naked-eyed objects. So this is Pollux in the constellation Gemini, Arcturus, and Aldebaran. But what I think is a bit more illuminating is how the sizes of these stars compare to the known separations between stars and planets. So what I'm showing here is the same plot I showed you earlier, except now I'm showing where the edge of the sun's radius extends to scale on this plot, which is not particularly interesting for the sun. But when the sun becomes a red giant star and starts to become as big as these red giants like Pollux and Arcturus and Aldebaran, you'll notice that its radius is going to increase to a substantial fraction of the radius or of the distance to Mercury in our solar system. And then when you look at all of these other solar systems, exosolar systems, you see that many of these planets are at distances that are going to be inside the future radius of their stars. So these guys are goners. But it turns out, from a planet's point of view, the story is even worse. And that's because you cannot neglect the force of tides raised on the star by the planet. Now, you're probably familiar with tides on Earth. This is due to the presence of the moon. the nice sloshy water on the Earth, it feels the gravitational attraction of the moon, which pulls it into this kind of bulgy shape. So in this case, I'm showing what the star looked like before you put a planet really close to it, which forms this tidal bulge. And this is due to the fact that the part of the body that is closer to, in this case, the planet, feels a noticeably stronger gravity than the far side of the same object. Now, if neither object were moving, this is what this situation would continue to look like. However, in general, the star is rotating and the planet is orbiting around it. Now, if the planet is going slower around the star than the way that this star spins, you'll be in the situation like you are with the Earth-Moon system. The Earth spins once every 24 days, the Moon goes around once every month, which means this tidal bulge of the fast-spinning, tidally distorted body tends to lead where the position of the body that's causing the tide is. And what this means is you kind of introduce a torque into the system. Gravity wants to realign this along a straight line to the planet. And so if you can think about the star trying to be pulled backwards, and I should say in this scenario, both things are rotating counterclockwise. So the gravity is going to try to pull this in a clockwise direction, which is going to slow down the star, give angular momentum to the planet, and push it outward. The Earth is doing this to the Moon. We are slowly pushing the Moon away from us, and we are slowly slowing down. However, if you're in the opposite rotation case where the star, in this case, is going slowly and the planet is orbiting quickly, the angular momentum goes in the other direction. And so the star spins faster and the planet gets pulled in closer. But then once the planet is pulled in closer, it actually raises a stronger tidal, it has a stronger tidal interaction, which means all of these processes happen much faster. And it turns out the planet will rapidly spiral into the star. And so on that plot that I showed you before, really you need to go 5 times the radius of the star. Those are all the planets that actually really need to be worried that it's going to fall into its star. So hopefully by this point I've convinced you that planets are going to be eaten by their stars. There's just no escaping it. So the next interesting question that we can ask is what exactly happens to these planets? And so I've listed here 3 different physical processes that might actually destroy your planet, break it up into bits, and do all sorts of fun things like that to it. The first one is tidal disruption. And this is the idea, again, related to the tidal effects, the fact that in certain gravity scenarios, the gravity on the closer side compared to the gravity felt on the farther side of an object matters and can be very strong. So in this case, if an object gets too close to a massive thing, that tidal stretching across the planet can actually just pull it apart. It'll be stronger than the energy that's used to hold the planet together. And we think that this is part of what can be responsible for forming rings around planets in our solar system. If small rocky bodies get close enough, they can be just tidally shredded and pulled to bits. A somewhat related phenomenon is one that's well studied in the study of binary stars, which is called Roche-Lobe overflow. And in this case, what you want to think about is the idea, when we think about space-time as being like a sheet of, like a rubber mat. If you take 2 massive bodies and drop them on, they form little gravity wells. And so that's what's illustrated here. So a more massive body has a deeper gravity well than a less massive body. And so this cutout is showing if you were looking down on the system and draw regions where the gravity potential feels the same, you get this bottom plot here. And you can see that close into to each of these objects, it's roughly circular. So you can imagine, so if this is a star and this is a planet, you can imagine that if the planet is big and puffy enough and becomes bigger than the region around it where its gravity wins, then the outer layers of the star can actually start to spill over from that object and fall down into the gravity well of the star. And so that's Roche-Lobe overflow. Now, the other scenario is that if the planet manages to avoid both of these scenarios and actually come in contact to the outer layers or even deeper layers of the star, then you're going to have processes such as ablation or vaporization, where you're just stripping off the material from the planet. So where do these occur? It turns out that some of the details of how and when and where a planet is destroyed depends a lot on how evolved the star is when it happens. So just to give you a sense of the difference of stars, here's an example of the interior of a sun-like star, which has a very thin convection zone. So the convection is the part of the star that's outside of the star, which is basically kind of boiling. And here is an interior view of a red giant star, which has a much deeper region of convection. Now, one of the interesting things to note is that when you do the calculations for things like the tidal disruption and the Roche-Loeb overflow, those calculations work out to be the same no matter what the mass of the star is. And so if you take a sun-like star and evolve it to a red giant, the point at which Roche-Loeb overflow occurs only depends on the masses of these things. And so in this case here, if the star is a sort of smallish red giant that hasn't evolved very far, you can see in both cases, the Jupiter will undergo Roche-Loeb overflow before it gets to the surface of the star. But if this is one of those much larger red giant stars, like I talked about, like more like an Arcturus or Aldebaran that is many times the solar radius, the Jupiter will actually can remain intact before something like Roche-Loeb overflow would occur. And similarly, for small compact bodies like the Earth, tidal disruption is a more likely way of destroying these. And even for the present-day sun, the Earth can actually plop itself into the star before something like tidal disruption would pull it apart. And so then you can start thinking about, well, in those situations, you now have to start thinking about ablation and vaporization as a process that will destroy them. So the next thing we want to think about is whether or not we can figure out if this engulfment of planets is happening, if we can identify stars for which this has happened. So I'm again showing that plot from the very beginning of the separation and masses of known exoplanets, except now I've color-coded the points differently. These black points here are dwarf stars. These are main sequence stars like our sun. Whereas all of these color-coded points are giant stars where we're using the surface gravity as a proxy for how large they are. And one thing you'll notice is that there seems to be an absence of very large close-by planets, which remember are the easiest to discover. And this could be potential evidence that we're seeing that any planets that may have once existed around these stars no longer do, and they may have been engulfed. There are some other signatures that we can look for. So again, stars grow very large when they become red giants. But one thing you have to remember is that angular momentum is a conserved quantity. And so I, especially now, based on Frank's story, I have to bring in the ice skating analogy that we frequently use for showing conservation of angular momentum. You picture a figure skater starting a spin, and when he or she pulls their arms in, they spin faster, and when you expand again, you slow down. So the kind of fun thing about this is that for angular momentum, the rate of rotation goes as a factor of the square of the radius. So in this case, if you take a star and increase its radius by a factor of 4, its rotation slows by a factor of 16. So now if you can then extrapolate in your mind to these even like 10 and 100 times larger, you then have to square those as well, so that you really expect red giants to be very, very slow rotators. On the other hand, if you engulf a planet, then that planet is dumping angular momentum back into the system and can spin the stars back up. And so that could be one signature. Another signature we could look for is pollution. And so by pollution, I have this little graphic here just to give you a sort of an analogy, is if you can imagine taking a little dropper of dye and dropping it into a beaker of red water or even clear water. The question is, how much do you need to put in for you to be able to notice it in the much larger sample? So you can imagine if you're putting a dropper of additional red stuff in, you're probably not going to notice, but if you drop in a color like blue, maybe you'll notice a little bit more. So by analogy, we can think about what the compositions of stars are compared to their planets to try to see, is there a way that we can determine whether or not the composition of the star has changed in a meaningful way. And the reason we might be able to do that is that stars are predominantly hydrogen and helium, like most things in the universe, with a very tiny slice of basically everything else on the periodic table. Okay, so let's now think, well, what happens if we try to drop a Jupiter in? Well, it turns out Jupiter is mostly hydrogen and mostly helium with a very teeny tiny percentage of everything else. So in this scenario, you can then imagine that you're basically taking a beaker of red that you're dropping into red material. So you're not going to notice anything. Earth, by contrast, is has a completely different ratio of abundances. Helium is practically non-existent on the Earth. That's actually how it got its name. It was first discovered by its spectrum in the sun. And so now you can imagine that you're dropping something that looks very different into the sun. But of course, one of the caveats here is that Earth is, of course, a much smaller thing. And so even though its composition is very different, there's the concern that maybe you still wouldn't notice because it's so small. And this is where the discovery of Kepler, or of all those things that are sort of sitting between the terrestrials in our solar system and the giants in our solar system, is very interesting. Because they could be scaled up versions of the Earth, which are much more massive, but still very chemically different fundamentally from their stars. You can also take advantage of special elements that happen to be relatively rare in the star. And this is actually a field that I study a lot. So what I'm showing here, this is again on a logarithmic scale, the relative abundance of all the elements of the periodic table as a function of their position. So we're starting at hydrogen, helium, lithium, beryllium, boron, and all the way down. This nice zigzag pattern is just due to the way that elements are formed in the centers of stars. But what I need to bring your attention to are these three elements, lithium, beryllium, and boron, which are very depleted in the sun. And this is because they happen to be destroyed relatively easily by what's called proton capture reactions at temperatures that are relatively cool from a star's perspective, which is, a few million degrees. Very chilly. But it turns out that our sun's abundance of lithium is very depleted from what we think started. So now what I'm showing here is if you take a sample of red giant stars and look at and measure their lithium abundance, the present-day sun, which we saw on the last plot, sits here. The red giant stars are fundamentally very, very lithium poor compared to that, and the sun itself is quite lithium poor compared to what we thought it was. So this line here is showing the lithium abundance we believe the sun started with. And we get this from measurements of the relative lithium abundance of things like meteorites in our solar system. And this lithium abundance is, again, on fundamentally on a logarithmic scale. So every time you step by a delta 1 here, you're stepping by another power of 10. So the sun has already depleted by nearly a factor of 100 from its current state. And red giants can be 10, 100, or even 1,000 times more metal poor, or more lithium poor than the sun. And to put that in perspective, some of these most lithium poor red giants actually have less total lithium than a planet. And so now, if you can imagine taking an observation of a red giant star, you might intrinsically measure a couple of different lithium abundances, and you can do the calculation of what happens if you start dropping Jupiters into them and add that lithium to the star. And you can see as you add more and more planets, at some point, the lithium abundance that you measure almost doesn't care about what lithium was originally there in the star, because the vast majority of the lithium atoms are actually coming from the stuff that you've dropped in. So this, I think, is something that's really exciting. But then the question is, all right, so now that we know these signatures, other than maybe not discovering planets close to stars, how do we go about measuring these things? And the way astronomers do this is by using the spectra of stars. So we take the light from a star and we break it up into the component colors. Now the energy and light that's created by the star happens deep within its core, and that light propagates out. And so right before that light leaves the star, it interacts with the very cool atoms and molecules in the atmosphere of the star. And these things absorb at very specific colors, which leaves behind these nice lines on your observed spectrum. So what we measure is the brightness along different colors, and we see the absence of colors at regions that tell us about the relative amount of different elements in the star. So here is a very, 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 very zoomed in part of that spectrum, looking at a very minuscule range of wavelengths. Of two stars that are nearly identical in every way. They turn out to be in the same open cluster. They have almost the same temperature, almost everything that you can think of. But if you look at all these little wiggles here, these wiggles are the absorption of light due to various elements. And I'm pointing here to the absorption due to the atom lithium. And so in this case here, this star has this very strong lithium feature and actually has more than 80 times the amount of lithium than this star here. And both of these are red giant stars. So it is, in fact, actually quite easy to measure very big differences in lithium abundances. Now, the rotation of stars is actually something that can also be relatively easy to measure. So what I'm showing here is the progression of what happens to a spectrum if you have a star that is rotating slowly and moderately fast and very fast. The lines of these stars get broadened. And the reason is that if your star is rotating, what I've done here is for this rotating star, I've color-coded it to indicate the red and blue shift that you get because you're looking at a star that's rotating. Part of the star is coming towards you, part of the star is going away from you. And each little region on the star is basically, you can think of as creating its own individual spectrum. But all of the spectra coming from this part of the star is going to be slightly blue shifted, and all of the part coming from this side of the stars are going to be slightly red shifted. You can't see that individually, you just see the sum over all those different regions of the star, and so the result is that you get these very broadened or very fat features that tell you the star is rotating quickly. Okay, so we expect high lithium and high rotation to maybe be an indication of planet engulfment. And this is something that I've actually started studying way back when I was doing my PhD, and this was one of the results that came out of it, where I went and looked at a big sample of red giant stars, and I measured how fast they were rotating, and I measured how much lithium they have. So here's that rotation from slow to fast here, and relative lithium abundances from practically none to lots on this axis. The blue dots here are the ones that were rotating faster than we thought red giants should be, and everything over here are relatively slow. And the main result of this was that if you look at the average difference between the two, on average, fast rotators have 10 times more lithium than the slow guys. And if you make a whole bunch of assumptions about how much mass is in the stars on average, blah, 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 you can kind of convert this to how many planets would you might eat, and the answer comes out to be a couple of Jupiters. However, you may notice that there is a very large scatter here of points, and I do have a little representative error bar. Stars in general can have lots of different lithium abundances for things that have absolutely nothing to do with planets, which is a problem. One of the things that it depends on is how much lithium it started with and how much lithium it destroyed, and both those things vary sensitively on how massive the star is. So one of the ways you can go around that is to try to get a sample of stars where you think everything is the same mass. So what I'm going to tell you about now is one of my favorite stories, the story of NGC 6819. And this is going to be a longish story about some of the really interesting things you can do when you combine information from all sorts of different methods of studying the same thing. So what's shown here is a color magnitude diagram. So this is basically like a Hertzsprung-Russell diagram. So this is the temperature or color of the star. So blue hot things here, cool red things here, fainter things in the visible here, brighter things here. The line here is showing what you would expect for a group of stars that all formed at the same time and are now all at a specific age. And if you remember from the very beginning, I said that when that happens, you expect a lot of stars to be on the main sequence, all of the massive stars to be gone, and the stars that are currently in the red giant phase will be all roughly the same mass. So all of these purple circles are the stars that are the red giants. We think these are all roughly the same mass. And this one star here, which appears to be right where you may expect, has a lot of lithium. In fact, it has more than 40 times the lithium than all the other giants. Now, I haven't talked to you too much yet about why red giants have so little lithium, but it has to do with this convection region in the star. So when the star is like our sun, it has a very thin convection region on the very edge of it, which is cool enough that lithium is fine. But some of that lithium gets mixed down into the star where it gets destroyed and is gone. But that's a relatively slow process, and so that's why the lithium in the sun has gone down pretty slowly. But below that region, basically there's no lithium left. And if you go even deeper in the star, there are some byproducts of the nuclear fusion that has powered the sun for its entire life. When the star becomes a red giant, this mixing region goes deep into the star, and so it mixes it into the lithium poor interior, and so that's why all the lithium gets diluted, and so it looks like the star has pretty much no lithium. And the important thing here is that it also brings up some of these nuclear byproducts. It actually changes the ratio of carbon to nitrogen in the star. And this star shows all the evidence that it has become a red giant, so we know this mixing has occurred, so we know it should be lithium poor. So that's important. So the first thing you can do is ask yourself, okay, how big of a thing would you need to drop in to explain the lithium that we see if we assume that it should have the lithium that all the other stars in the cluster do? And when you work them out, it turns out to be a small star, which is a problem because a small star also burns its lithium, so it's not going to supply any lithium, so that actually doesn't work at all. So that's a problem. Another potential problem is that, so that lithium-rich star was discovered in 2013. 2 years previously, there was a paper that brought up the possibility that this star may not even be part of the cluster. So this was an astroseismology paper. I'm going to talk a little bit more about astroseismology in a minute. But basically what they were doing is they were trying to show that there is this oscillating parameter, which is shown on this bottom axis here. And the point of this was to show that it correlated very strongly with the brightness of the stars in each cluster. And so they're like, hey, here are 3 different clusters at different distances. If you measure this oscillating parameter, you can very easily tell which guys are part of the clusters and which guys aren't because they fall in this nice tight relationship. And so this is the lithium-rich star. They classified this one not knowing that it was lithium-rich. They're like, hey, it's probably not a member. But the problem is that if you believe that, you have to ignore a lot of other evidence that says otherwise. So when you look at the star cluster, if you believe everything in the cluster belongs together, they're gravitationally bound, you expect them to all move together. And if you look at how the star is moving in the proper motion, so this is on the plane of the sky, it's moving the same way as all the other stars. If you then measure that third parameter, the velocity towards or away from you, it's also moving the same way all the other stars are. So this is just showing the distribution of the radial velocity towards or away. It's pretty much spot on exactly where you expect. I also showed you that, in terms of the color and brightness, it's also where you expect. So how does this thing that looks in every way you can think of like it's part of the cluster not be there? And then, even better, this was not available to us at the time, but Gaia measured a parallax for the star. It is at the distance to the cluster. So it's at the same spot, it's the right brightness, it's the right everything. How on earth is it this astroseismology parameter weird? Okay, well let me explain to you a little bit of, about astroseismology. So if you think about a star, the star is not just sitting there. It is actually oscillating up and down as waves of various types propagate around the star. So this, as my 3-year-old calls this, the squishy star, it's doing lots of things. And as the squishy star pulsates, what ends up happening is that the star is actually slowly increasing and decreasing in brightness. And so if you stare at a star and watch how it increases and decreases in brightness for a very long time, you can figure out the modes at which it oscillates. And so this is kind of like ringing objects, ringing bells, right? So they will make a particular sound depending on how big they are and what they're made of. And that really, if you could break it down, is a whole bunch of different modes of oscillation. And so you can do the same thing for stars by looking at the light. And so what I'm showing here are power spectra of 3 different types of stars. So this is the oscillation frequency so this is low frequency, high frequency, and then this is how much power is in each of those frequencies. And if you're able to tell that there is this cluster of lines here that moves slowly from the high frequency to the low frequency, you have just measured the change in the surface gravity of these 3 stars. So just like how very large things have that low, like gong kind of noise, but a smaller object has a much higher pitch, your smaller stars will ring basically at higher pitches, and the smaller ones will have a much more low frequency. So you've just measured change in surface gravity. Congratulations, you're an astroseismologist. And so you can use that information to actually very precisely measure the mass and the radius of the star independent of the other things that you usually need to know. And what we did is that we compared that to the expected mass and radius of the star if you assume the star was in the cluster. And so we find that the radius comes out to be roughly what we expect. But this astroseismology is really telling us that the star is actually significantly less massive than you would expect. And yet it's still a red giant. And our best explanation for what is going on is illustrated by this crosscut of what's going on inside of a red giant star. Again, you have this very deep convection zone. You have this tiny core of helium. You have a little bit of hydrogen burning shell going on. So you can imagine if this thing had a companion that it interacted with, As the star had expanded, the outermost regions of the star are the least dense, so perhaps as the planet went in, it was able to strip off the least dense part of it and then eventually get destroyed slightly deeper in the star and mixed up all of its material in there and enriched the star. Now, if you're thinking, well, how's the star still the same size if you take off all that mass? I had that same thought, but it turns out one of the funny things with stars that are structured this way is that the radius of the star actually really only depends on how much helium you have in the core, which really has absolutely nothing to do with the planet. So if you strip off all the material, the star actually kind of bounces back a little bit and would still be roughly the same size. So our leading hypothesis then, when we pull all of that information together, is that the star has lost a lot of material. And so now if you run the calculation of how big of an object do you need to explain the lithium, you're at least well within the range of not a star. Not quite a planet either, so this is a brown dwarf size. So this is something about 45 times more massive than Jupiter, but it's still something that you expect to have a lot of lithium in it. That's one of my favorite stories. So the power of combining all these sorts of things together. I'm going to go a little bit quickly through this next part just because I'm running short on time. But this idea that planets can help strip the star is something that is an idea that's been around for a while. The Kepler mission has discovered some interesting things where they have found what are called these B subdwarf stars. So these are things that are hot, but significantly less luminous than you would expect them to be for other types of normal types of stars. And what we think they are so we have our sun converts hydrogen to helium in the core, and then later the helium will eventually start to fuse into higher things. But if you strip off the atmosphere, you can actually stall that, and the helium core will never start fusing helium. So we think these things are the bare helium cores. And so in this case, what was discovered is this Jupiter mass thing orbiting at almost twice the separation that Earth does to our sun. And the prevailing idea of what happened is that it was once closer, and when the star became a red giant, it actually helped strip off the atmosphere. And once that mass was gone, the orbit of the planet expanded. There's another example where these very, very tiny things, so now like half an Earth mass things, were found around another type of these stars. And in this case, the scenario that is thought that these were once giant planets like Jupiter orbiting closer. And so in this case, when they interacted with the star was much smaller. It wasn't quite as giant of a red giant. And so these planets went into the star where some amount of ablation, evaporation happened. So they lost some of their atmosphere, the giant lost some of their atmosphere, and so we now have cores orbiting cores. So planet cores orbiting the cores of a red giant star. All right, so looking ahead, a lot of the results that I talked to you about have been made possible by the wonderful Kepler mission. So Kepler, which is, sorry, I keep losing the pointer here. So the Kepler telescope had this big sensor. It pointed during its prime mission at one location in the sky for 4 years continuously. So this is just showing a zone of the part of the galaxy that was covered by Kepler. And the reason for this is we needed the long time baseline where they were trying to discover Earth-type planets orbiting sun-like stars. But one of the great things that came out of it is this very long time series observations of all these stars and how their brightness was changing over time, which led us to all this astroseismology things in addition to the prime mission. The downside to that is to make the mission as effective as possible, it had to avoid the brightest stars, which would saturate a lot of the detectors, and really focus on large numbers of fainter stars, which unfortunately makes it very hard to follow these things up. And so the future, which is also the today, is the TESS, which is the Translating Exoplanet Sky Survey, which is doing a complementary search. So instead of Kepler, looking in one area for a long time, TESS is spending 1 month covering the whole sky. So its camera looks like, the spacecraft looks like this. So it has four lenses. And it covers actually over 90 degrees in one pointing in one dimension. It's covering over 90 degrees at once. And so what it does is it stares at the sky for 27 days and then steps over and then does that every 27 days. And then it'll do a 180-degree flip and it'll do the other half of the sky. And so right now, this is upside down from our normal perspective because it's working in the southern ecliptic pole. And so right now, I think it's on sector 10 or 12, and then it'll eventually flip over and do the north. And And I should also point out that Kepler's extended mission, when after it broke a little bit, it could only point along the ecliptic plane. And you'll notice the ecliptic plane here is actually the one place where TESS is not covering, so it's actually very complementary in that sense. And so the goal of this is to really get the brightest stars. So the stars where we already know that there are planets around, where we're going to discover new planets that are going to be very easily accessible to the James Webb Space Telescope, where every photon counts, so we need things that are bright. So we are already getting data from this mission. The first 2 sectors of data are now publicly available. Anybody can look at them. And again, in terms of current data taking, it's almost done with the first half of its mission. And there are some other really important complementary missions that are coming up. So you've heard a little bit about Gaia already. Gaia is basically measuring the positions of stars very precisely. It gets the distance doing parallax. So this is the idea. If you hold your finger up and blink your eyes back and forth, things close by move a lot, things farther away not so much. And so Gaia uses, looks at the sky here, waits 6 months until it's on the other side of the sun. And so far, it's had 2 data releases. It's given us precise positions. The most recent data release gave us parallaxes. As it continues to look at these stars over and over, it'll start to show the proper motion. So this is how the relative motions of stars due to the orbits of the Milky Way. And then if they have companions, either stellar or substellar, then they'll also have orbital wobbling on as their companions do the dance. And so you can get these very complex motions when you add all these things together. And then I'm a spectroscopist at heart, so I have to talk about spectroscopy. One of the projects I'm working on is called panoptic spectroscopy from the Sloan Digital Sky Survey 5. So this is using 2 telescopes in both the north and south hemisphere to look to obtain optical and infrared spectra, high resolution of, like everything. Not quite everything, but a lot of stars. There's 3 major programs. I'm involved in the Milky Way Mapper, so this is studying stars in the Milky Way. It's building on the ongoing Apogee 1 and 2 surveys, which were part of SDSS 3 and 4. So this map is just showing an artist's rendition of what we think our Milky Way looks like, and this is showing density coverage of what Apogee 1 and 2 is get, and then the very ambitious of Sloan 5. And one of the components, which is actually the part that I'm working on, is we want to do radial velocities, and so go back and measure over and over the velocities of stars to learn about the companions, both big, small, everything in between, around these stars. So just to wrap up, like I said in the beginning, I think the time of big data in astronomy is actually now. We've really started. We have a lot of eyes in the sky. There are missions that I haven't even talked about where we're getting a lot of complementary all-sky coverage. We have all-sky coverage. We're taking images, we're looking at spectra, and it's really going to give us a lot of new information about things we've never dreamed of, and a lot of new types of planets we're going to discover, a lot of good follow-up for our upcoming missions like James Webb. And what I think can be really exciting is the fact that once you start looking at such large number of things, you start to increase your chances of finding these very odd systems that can actually teach you a lot about the kind of universe as a whole. So thank you. Okay. All right, questions? Yes.
Kind of coming back to our solar system, I read somewhere once that the gas giants actually moved around and out there.
So I'm going to repeat the question for the webcast, and then we'll use the microphone. The question was, I've heard that planets in our solar system moved around a bit. Can you comment on that?
Yeah, so I actually know a little bit less about what we think happened in our solar system, a little bit more about what we think happened in other solar systems. Because, again, the discovery of the hot Jupiters was completely unlooked for. It was one of those things that we see there and you're like, nah, that can't be right. Like, we must be doing something wrong. And from that, we have gotten the sense that there just wasn't enough stuff close to the stars to form something that big, so they had to have come from somewhere else. And so they really led observationally led our theories, because we had a beautiful theory of how the solar system worked. It made sense. And then we found other planets, and it just threw everything out the window. And so now we know that things have to be a lot more dynamic. I have heard of models that showed that, particularly the outer planets had to have interacted a bit. I know less, unfortunately, about the details of those interactions, so I can't comment on them any further. Sorry.
Do planets ever get flung outside of its star's orbit?
Absolutely, yeah. And so that is something that I think is a bit more common when you have other stars. Well, 2 times, actually. So early on in the planet formation process, when you are building up the planets, you have lots of things that could become planets, and they interact gravitationally, and some things get flung out. But then the other place where it can happen is when you start having other stars involved, which, as I and many other astronomers like to talk about stars as if they, exist in isolation, but we actually know that the vast majority of stars come with siblings, and so those processes are common. So yes. Other questions? In the back.
You had mentioned earlier in one of your PowerPoint slides that it was possible that Earth was a red giant beforehand. Does that make it possible that we may have more Earths within our own solar system?
I'm sorry. I said before that I missed the question.
My question is that you had mentioned that Earth was at one point possibly a red giant. Is it possible that the red giants that are existing in our solar system right now may become another Earth?
So I guess the question is, so in our solar system, whether or not the Earth goes into the sun Earth is kind of on the hairy edge, so we're not sure. But is your question more along the lines of, can some of the planets around these other stars be habitable like the Earth?
Yes.
Yeah, okay.
Thank you.
I was just making sure I understood. Yeah, so it certainly is possible, right? So as the sun gets larger, becomes a red giant star, it's going to get really hot here. But for colder planets, right, maybe that's a good thing for things like life. And so you can imagine that in planets around red giant stars that were once very cold, they could potentially become Earth-like. The problem with that, it could happen, but the difficulty for any life there is that the red giant phase is very short, and the star actually changes very rapidly. And so any conditions that are suitable for such things to happen, it will rapidly go away, and then they're toast again.
As you mentioned, as you explained, this transfer that sometimes happens between a star and a planet, is there any possibility, and if that's a possibility, is there any evidence that might happen between planets of different mass, that they can actually kind of suck out some materials into another planet? Or
Oh, that's interesting. Again, I think definitely in the planet building phase, when there's a lot of gases around, that's how some of the planets win and become planets, and the other things become not planets. Is that the things that kind of build up the quickest then start hoarding all the resources, and then they become the dominant thing and kick everyone else out. They're kind of tyrants in that way, I guess. But I think once things are in more stable configurations, I think it's a lot less likely, just because the relative sizes are pretty similar, and so I think it's harder.
Yeah.
I'm not sure, but I think it's harder.
Okay, we have a question from online. It says, when the sun expands into a red giant, will the gas giants of moons like Europa, Enceladus, or Triton become habitable?
Sadly, I haven't done that calculation. That's a very interesting question. They will, yes, they will get,
It's not going to be habitable.
will not.
Go.
Yes, that's a good question. They will get warmer, but I actually haven't thought about by how much. That's a great question. I'm gonna have to go do that.
Okay.
But again, going back to the other question is, even if they do, it will unfortunately be short-lived.
Yeah.
Yes.
Wait, but it's still like 100 million, I mean, a million, about 10 million years for the red giant phase?
Yeah, but so I'm going to show a little bit of my biology ignorance. I mean, for bugs, great, but for people, not so much.
Are there planetary systems in binary star systems, and what is their prognosis?
Their prognosis is a lot more complicated. Now, I know there are two types of stable orbits that you can have. One is where the stars are more tightly bound and the planets orbiting both. So this is like a Tatooine, if you're a Star Wars fan, a Tatooine style where you get two suns in the sky. If my recollection is correct, I think that is of the stars that we know, that might be the more common one. Whereas having the planet around, one object where, the star, the other star is very far away, I think those tend to be very, very widely separated. In which case, you can mostly treat them as, as a single point, but there's a lot of interactions that actually will sculpt the planet-forming disk and will affect the resulting inclinations of the system. So actually, one thing that they think is that when you find, in our solar system, right, you have the sun rotating, all the planets going around, all in roughly the same plane in the same direction. They have found instances where you have a star that's rotating like this and a planet going like this, which is, how did that get there? And one of the ways that you can do it is that if you do have a wide binary that is on sort of that similar inclination, it can force the angles of orbit. And so I know there's evidence of that. But yeah, it gets messy very quickly once you start adding more things.
Other questions over here?
For perspective, can you tell us quickly about some of the interesting orbits that some of these like hot Jupiters that they're orbiting their stars in like less than 2 days?
Yeah. Yeah, so it's short. And actually, so one of the things I didn't, let's see if I can do this super quickly.
And what else interesting have you found out about some of these exoplanets in terms of their orbits?
Yeah, so one thing that I didn't really talk about, but which I think is really cool, and there are a lot of things like this, but so this is down here, this is the Kepler 11 system. So to scale, this is the separation of 6 planets around Kepler 11. All 6 of these are more massive than Mercury, and all 5 are inside Mercury's orbit. So so this is like really stuffing like basically as many planets as you can. And this comes back to the question of, then they started interacting with each other at this point. And actually because this is actually surprisingly not that common, you can confirm and actually measure the masses of these things because these are close enough and big enough that the gravitational interaction between the two is measurable. And so you can see that their orbits are being perturbed a little bit by the fact that, okay, it would normally be on this orbit, but now the next one out is about to pass it, and so it's going to tug back a little bit on it, and it affects the dynamics. So we find things basically as packed together as to the point of like just barely being dynamically stable. Where if you try to put one more thing in there, and then it's all going to scatter. So I think that's one really cool thing that's come out of it.
I will say that online we had a little chat about where these hot Jupiters formed, and that the standard idea is that they formed out where our planet, our Jupiter is now, but they migrated inward. And one of the questions that sort of came up was, all right, well, what stops them if they're migrating that far inward? What stops them from just crashing into their star? I mean,
yeah. So I don't know that we've answered that question necessarily, but one of the things that's important is that So this migration happens while the disk of material that forms the planets are still there. And so if you can truncate the disk and get rid of that material, they basically get all the way into where the edge of the disk is, and then there's nothing else for it to interact with, and so it can stop. But I know that was certainly an early problem. I don't work on the models myself, so I don't know how solved that is, but that was actually one of the things that came out was like, okay, great, we now understand how we can make them move, but how do we stop them? And one way is to process these that truncate
Or
the
perhaps
disk.
the T-Tauri wind just blows all that stuff out.
Right, yeah, so it's another way of, clearing out the region around the star, whether by processes, from the star, could be the wind, could be magnetic fields, I think have ways of, stopping the material from going directly to the star.
Okay, do we have one last question? We do not. All right, so next month, learn how to recycle your used pulsars, okay? And do gamma radiation. Let's give Joleen another hand.